All right, everyone. Good afternoon, good morning, and good evening, everyone. So welcome to the latest Autoware Center of Excellence Safe Autonomy seminar. It's our great pleasure to have Dr. Yash Pant from the University of Waterloo to present his research on a very exciting area of motion planning for multi-agent systems using, formal logic such as signal temporal logic objectives. And so Yash, he leads the control learning and logic group in University of Waterloo's Department of Electrical and Computer Engineering. He received his PhD from in electrical engineering from University of Pennsylvania, actually with me, and then he followed on with a postdoc fellowship in University of California at Berkeley, and before joining Waterloo. And his research focuses on decision making for multi-agent systems, autonomous systems, and he works at the intersection of control theory, machine learning, formal methods, and optimization. And his interests are in applications to ground robots, human-robot interaction, and swarms of aerial robots. So, welcome, Yash. We're very excited to hear about your research. And everyone, please feel free to ask questions at any time. This is a very informal talk, and we are here to learn.
Thank you, Rahul. Thank you for the introduction, and thank you for the invite as well. Right. As Rahul said, it's a pretty exciting area because I guess it started in his group, so should be saying that. Right. Today's talk is going to focus on essentially motion planning for multi-agent systems, given the complex behaviors encoded in signal temporal logic. As Rahul said, I run the control learning and logic, or the control logic and learning group. The order of the L's doesn't matter, at the University of Waterloo, where we focus on behavioral planning for multi-agent autonomous systems with complex objectives, operating in evolving and uncertain environments. And the video over here just shows us a few examples of things that we've been working on. Probably we're interested in these three research areas or three application areas.
Oh,
And I
Yash,
draw on tools
I
from,
feel like your
sorry.
audio might be breaking up. Maybe you can,
Oh,
yeah, just check it or turn off the video.
right. Let me see.
It seems to be okay
I'll
now.
turn off the video. Is that any better?
Yeah, try. Go ahead.
Okay. Right. So yeah, we draw on elements of control theory, formal methods, and machine learning to work with these three problems. And today's talk is going to be mostly focused on multi-robot and autonomous system problems. The motivating problem for what we're looking at over here is the scenario of urban air mobility, or this near future scenario where we'll have hundreds, if not thousands, of manned and unmanned autonomous aircraft systems operating in dense, cluttered urban environments that are going to be evolving and will have a whole host of rules applied on these airspaces. So in today's talk, I'll first look at how do we formalize the type of requirements that we expect these autonomous systems to have with temporal logics. So I'll introduce us to signal temporal logic, and I'll then introduce formally what the motion planning problem looks like with STL specifications. Then I'll move on to the problem of robust multi-agent motion planning with signal temporal logics, which is how do you actually solve this motion planning problem. We'll first start with a centralized trajectory planning method called flyby logic. Then I'll talk about how do you get stronger guarantees for the type of nonlinear dynamics that you expect these aircrafts to have, and co-design a trajectory planner and a controller. And then we'll also see how do we operate in a setup where each agent is allowed to make its own decisions, but they can coordinate with each other. So we'll talk about a distributed trajectory planning method. After that, I'll move on to some ongoing work, and based on how much time we have, I'll see how much depth I can go into in that. All right, so first let's start with signal temporal logic. As a motivating example for what we're going to do, consider the scenario over here, where I have four crazy fly robots. Think of them as being in teams of two each, where the red and blue robot are one team, the green and black robot are another. And their task is to visit these virtual goal regions, which are on the top left and bottom right of the screen, every 6 seconds. So they need to be, as a team, they need to have visited this goal set within the first 6 seconds. Then they go to an opposing goal set in the next 6 seconds, and they repeat this process twice. These robots should, of course, do that while making sure they don't fly into this virtual unsafe or no-fly zone in the middle, that they stay within the confines of this motion capture area, don't crash into each other, and so on. So of requirements like this, we'll see how we can encode them efficiently using signal temporal logic. And then our techniques will essentially allow us to generate trajectories that allow these robots to satisfy these type of requirements. So on the top right of the screen is a simulation. That's the video in video. The main screen shows an experiment. And what you see is that what the robots in the experiment are doing is exactly what's happening in the simulation as well. So that's part of the strong guarantees that we aim to get from our methods. This work was done when I was a grad student in Rahul's group. So this is a lab at the University of Pennsylvania where we were flying these crazy fly robots. And now we are recreating this type of a setup at the University of Waterloo as well. All right, so how do we actually use signal temporal logic to encode these type of mission requirements in a mathematically sound manner? So STL is a behavioral specification language. And I won't get into the details of the grammar of this language, but for our purposes, you can think of it as a logical formula that has some elements that allow us to reason over continuous time trajectories that take real values. For example, let's say I have a safety specification over two quadrotors. Let's say their positions are Q1 and Q2. And my requirement is that I don't want them to crash. I can encode that using the always operator in STL. So a logical formula phi1 that at the end of the day will evaluate to either a Boolean true or a false. In this case is evaluated based on the always operator, which is active in a time interval of 0 to 10 seconds, where I'm saying that I do not want, so that's the logical negation, the position of quadrotor 1 to be inside the unsafe set. And this notion of a position or a variable being inside a set or meeting some inequalities is what we call an atomic proposition, or the smallest building block of an STL specification. I can also say the same thing for the second quadrotor by using the logical and or conjunction. And I can also encode requirements such as that I also don't want these two quadrotors to be anywhere close than delta meters to each other. So we can encode safety requirements pretty naturally in STL. You can also have requirements that require the robot to do something more than just being safe. For example, with the eventually operator, we can say things like, within some time interval, I want these two quadrotors to reach a goal set. Imagine they're trying to do a package delivery type of a problem, where this formula phi2 is now saying, we look at the eventually operator, again, acting in the range of 0 to 10 seconds, but I want quadrotor 1 to be inside the goal. And also eventually within time 0 to 10, I want quadrotor 2 to be inside the goal. So at any point in time between 0 to 10 seconds when quadrotor 1 reaches the goal, the first part of the specification is true. And similarly, if the quadrotor 2 reaches the goal at any point within 0 to 10 seconds, the second part of the specification is true. The logical AND of them will result in the entire specification being true, only when both the robots hit it inside the goal set. We can also have if-then type of requirements in STL. So shown over here is example of using a logical implication, which says eventually within 10 seconds, quadrotor 1 being inside the goal should imply that it's dropped package P1. And similarly for the second quadrotor. Now in STL, we can take these individual specifications, put them together, and we can nest operators. We can do a whole lot of tricks. We'll see a few examples later on. But let's say I put them all together using the logical AND. So I get a mission that says, be safe, reach a goal set, drop a package when you get there. So that's the specification psi. And the specification has a time horizon to it. For each of these operators, you would have noted that they were active between a time interval of 0 to 10 seconds. So I have a specification horizon of 10 seconds, which means I need two quadrotor trajectories of duration at least 10 seconds before I can evaluate the specification to be true or false. So that was a quick introduction to how signal temporal logic can be used for reach avoid like problems. We'll of course look at more richer problems later on. And in fact, STL can encode a whole lot of complex behaviors very naturally inside that. But now let's assume we know how to encode our requirements in STL. So the question is, how do we make these robots actually satisfy these requirements? And that's our motion planning problem. So an STL specification, if we were to think about it as a function, it takes in this continuous or the real value trajectories over all UAVs or all overall autonomous agents and maps it to a single Boolean true or a false value. True if all parts of the specification are satisfied, otherwise it's false. Our control problem then can be thought of as a finite horizon discrete time problem, where I take my specification horizon from, let's say, 0 to 10 seconds, as in the previous example with two quadrotors, and I discretize, let's say, uniformly in time. What I want then is a feasible solution to this problem, where I want to find a sequence of control inputs for each of my robots. such that the resulting trajectories over all of these robots satisfies the STL spec, or the STL spec evaluates to true. So that's what that notation over here is saying. Of course, I want to make sure that I pick those controls such that the trajectory respects the UAV dynamics. There's no point picking controls that the robots can't actually fly out. And also, I want to do this while respecting constraints on the system, such as robots have a maximum thrust, maybe upper bounds on or lower bounds on velocity, accelerations, orientations, and so on. So if I can find a solution to this problem, I've solved the problem of generating trajectories that satisfy STL specs. But of course, if it were the challenge is how do you encode this particular problem in a way that it can be solved efficiently? And in order to take a look at that, we'll have a very coarse-grained look at some of the related work. So the most popular line of works in coming up with controllers to satisfy STL specifications is to turn the problem into a mixed integer programming one, where the idea is you introduce binary variables for the smallest building blocks or the atomic propositions that say whether a state was inside a set or not. Then there are ways of automatically generating mixed integer constraints such that if you satisfy those constraints, you've satisfied the underlying STL specification. One of the challenges is that these usually rely on mixed integer linear programming as the underlying solver. So they're restricted to linear systems. We've shown in some of our previous work, and this is by now well known, that these methods do not scale well because mixed integer programming itself does not scale that well. And they also produce solutions that have a problem of zero robustness. We'll define robustness later on, but that make them difficult for implementation in a realistic system. Another way of solving these problems is to actually abstract away the continuous part of the dynamics and work with a discretized workspace with simplified motion primitives. There are challenges over here as well that these methods do not scale as you add multiple agents, or especially if you have three-dimensional workspaces. And also the type of specifications or the type of problems you can encode and solve with these methods are relatively limited. So there are some references on this. So at the heart of it, the state-of-the-art approaches, or at least the most common ones, are combinatorial approaches that do not scale. And this kind of motivates what we want to do. I would be remiss if I do not talk about some more modern methods. So people have looked at solving this problem via reinforcement learning. The challenge there is that, of course, it relies on breaking the problem down into a very simple, discrete abstraction one. It's also limited in the type of specifications that we can have. There's methods that can turn this into a purely convex optimization like problem. But challenges over there are that they again rely on high dimensional polyhedral projections, which means if you have a complicated specification or a long time horizon, these methods just don't work computationally. At this point, I think the methods that are finding the most applications in this area are based on control barrier functions. But their limitations are that first, they rely on handcrafted control barrier functions, and also they're limited in the grammar of STL or the types of specifications that we can encode using or solve for using control barrier functions. So anyway, with that, we can move on to the core idea behind our approach, which is that instead of solving a combinatorial problem like a mixed integer program or a graph search or find a policy over an automata, what we want to do is we want to solve a continuous optimization problem. And in order to do that, we rely on the notion of the robustness of an STL specification. So associated with signal temporal logic, just like we have the Boolean semantics that map a trajectory to true or false, we also have robust semantics, which now, rather than mapping them or having a discrete outcome where a trajectory gets mapped to a true or a false, we have a robustness function that can be automatically constructed from a given specification. And now it takes in the same input as the specification, which is your real value trajectories, and maps it to the extended real line. This mapping has a nice property that if the function evaluates to a strictly positive value, it means that the underlying specification is satisfied. Otherwise, it's not. So we're going to rely on this notion of STL robustness, which we can also interpret as a degree of mission satisfaction. So if you have large positive robustness values, means you can tolerate a lot of deviations or a lot of disturbances at runtime, for example, wind or even small failures. On the other hand, if you have very negative values of robustness, it means you've done a great job of violating the specification, which for our problem is a bad thing. And if you have robustness close to zero, then any small disturbance could make your system violate a given specification, which is usually the problem with mixed integer programming based solutions. So we'll try to essentially find trajectories that lie on the right of this type of a figure. Before we get into how do we actually generate those trajectories, let's take a look at how do we build this robustness function through one example. And my example would be that of a safety specification. So the specification says that always in a time of 0 to 10 seconds, I don't want quadrotor 1 to be inside this unsafe set U1 or to be inside this unsafe set U2. So it's a simple safety specification. What we can also do is just following the robust semantics of STL, build up the robustness function, where based on this always operator, we have a corresponding minimum operator that's going over this time range of 0 to 10 seconds. Corresponding to the logical OR, I have the max operator showing up. There's a minus sign over here because of the negation. And then in order to quantify how well or has my atomic proposition or the position being inside a set being satisfied, I have to introduce a distance metric. So we usually introduce a signed distance metric, could be in some n-dimensional space. And then if I plug in my trajectory into this function rho of phi, I'll get a real value. I'll get a real valued output from it. In fact, we can build such a specification, such a function for any STL specification automatically. So that's just following the robust semantics. And if the resulting value, let's call it R, takes on a strictly positive value, a physical interpretation of that is that I can build a tube of radius R, where again, this radius is with respect to the same distance metric that we're using over here, such that all trajectories that lie inside a tube of radius R are going to satisfy the specification. So which means if I plan out a trajectory as shown by this black line, but I have disturbances in the system, as long as those disturbances don't push me outside of this tube, I'm guaranteed to satisfy the STL specification. So which is why this kind of naturally is called a robustness function over here. So then this robustness function, we know large values mean you've satisfied the specification. The more positive values you take, the more robustly you've satisfied a specification. So intuitively, all we want to do is find trajectories that maximize robustness. We have in the previous slide, now we have an algebraic expression for robustness as well. So we could throw it to an optimization solver. But turns out we can't just do that in a very straightforward way. There are some challenges. The first is that this robustness function is not smooth. Because of the discrete max and min operator, we have discontinuities in this. Also, the sign distance operator is not necessarily smooth. So gradient-based approaches do not work. So we're back into a problem of mixed integer programming, which does not scale. Also, robustness functions for any interesting specification, it's going to be a non-convex function. So, or non-concave function. So maximizing it is not going to be straightforward. One of our earlier works actually addressed the first three problems, and we came up with this continuously differentiable notion of robustness, which we call smooth robustness. So going forward, now we'll assume that given an STL specification, I actually have a smooth robustness function associated with it. And smooth over here just means that it's continuously differentiable. So then gradient-based approaches can be applied. And one of the methods that exploits this smooth robustness was a work that we did called flyby logic. Again, the fly over here tells us that we're looking for is that its applications are based on aerial robotics. What we want to do over here is come up with an optimization that is non-convex, but still efficient in, or something that we can solve efficiently based on maximizing smooth robustness through the problem of only selecting waypoints for robots. So again, smooth robustness over here is a function that has a nice property that if it evaluates to a positive value or a value greater than a positive threshold epsilon, it means the underlying specification is going to be satisfied. And what we want to do is not find low-level control signals like roll, pitch, yaw, and thrust for the robot, but only find high or lower dimension waypoints such as positions and velocities, and that too in a sparse manner through the map so that our resulting trajectories can satisfy the specifications. So flyby logic is actually a way of encoding this in a way that we get some strong guarantees on the solutions that we get out of our optimization. So the problem setup is as follows. So our optimization variables are n+1 waypoints per UAV. Again, think of each of these waypoints P0, P1, and so on to be uniformly apart in time. For example, it takes me 1 second to go from P0 to P1, 1 second to go from P1 to P2, and so on. So again, if I know the specification horizon in seconds, I need to have n such that n times TF, which is the time between waypoints, should be greater than my specification horizon. But just having these low frequency waypoints is not going to be enough. I also need to think about how are these waypoints being connected by these robots when they actually fly it out. And what we're going to do is we're going to connect these waypoints using jerk minimizing splines for multi-rotor robots. So that's a work that was published by Muller et al. From ETH Zurich in 2013. We take those type of jerk minimizing splines, and what we actually show is that the closed form expression for this trajectory discretized. So the red stars over here are the intermediate points on the jerk minimizing spline that are connecting these successive waypoints. These red stars over here are actually closed form linear functions of the preceding and succeeding waypoint. And so what I have is essentially, if I move my waypoints, I have a nice linear function that tells me how the rest of the trajectory in the position, velocity, and acceleration space is going to move. And so what I have is a representation of the entire trajectory at a high frequency rate using very few variables, which are these waypoints of interest. So there's a lot of linear algebra that goes into it, but in the interest of time, I'm going to skip that. With this, we can actually formulate our optimization problem, or the flyby logic optimization. It's a centralized optimization, so it's the same optimization being solved over the variables for all the drones, even though I explained this only using a single UAV in my examples. But if I had multiple UAVs, just imagine I have a copy of these waypoints for each of the UAVs. So the waypoints are going to be our optimization variables. What we're going to try to maximize is the smooth robustness over these high frequency trajectories that we saw in the previous slide over all the UAVs. Then for each UAV, for each time step, I'm going to have a constraint or a set of constraints, but it turns out I have constraints only on how far away successive waypoints can be from each other. And what I work out are these functions LB, UB for velocity, acceleration, and jerk, which actually turn out to be linear functions in the velocity at the waypoint at which you started off. So what we have over here is, if my waypoints satisfy this constraint, then I have these linear functions that tell me that my velocities, accelerations, and jerks are going to be within given upper and lower bounds. So one of our main contributions was actually proving that these constraints work. And finally, the last constraint over here is that in order for the optimization to actually find trajectories that satisfy the specification, I want the smooth robustness to be over some positive threshold epsilon tilde. In general, this is a non-concave optimization. So based on, if you have any STL specification of interest, like the one that we saw for the two UAVs trying to deliver a package, that would result in a non-concave objective to be maximized. But because we have very few variables and we have nice and linear constraints, this can actually be solved via gradient-based methods. And we'll show you the experimental results for that in the following slides. But anyway, if I find a solution to this objective, if I find a solution to this optimization, what I've done is I've generated trajectories that are going to give me guarantees on continuous time satisfaction of the underlying specification. That is, even though I work with just these waypoints that are at order of seconds apart, even the continuous time trajectories are still going to satisfy the underlying specification. Also, these continuous time trajectories are going to be kinematically feasible. That is, if I know that my robot can track trajectories that have bounded velocities, accelerations, and jerks within some given bounds, these trajectories are going to respect those given bounds, so they can be flown in a straightforward manner. So now we'll take a look at some experimental results that show just exactly how well does this work in practice. A benchmark problem is going to be a simple reach avoid one, where I have multiple UAVs. Let's say I have capital D UAVs. All of them should avoid an unsafe set, shown over here. They should always reach a goal set, shown on the far side. And we should do this, of course, making sure that these UAVs don't crash into each other. There's also other velocity and acceleration constraints, which I'm not showing over here. So a reach avoid specification like this can be encoded as shown below in an STL specification. So the highlighted parts with the different colors correspond to the different parts of this objective, like avoiding an unsafe set, eventually reaching a goal set, and also always maintaining a minimum distance, at least a minimum distance between the UAVs. So something like this we can solve using flyby logic. Over here is an experimental evaluation of the trajectories that were generated by flyby logic and then flown using onboard controllers. We have 8 UAVs, and the goal set is on the far side of the room, and in the middle of the room is the unsafe set. I apologize for the low resolution. I'm not sure why it's so low, but what you see over here is that all 8 of the UAVs, they do indeed make it inside the goal set within the first 6 seconds. We see this behavior emerge that Some of them make it inside the goal set first and then head out, letting the others enter. And we don't actually have to schedule any of that. This happens naturally as a part of solving this optimization, and it results in these trajectories that can be flown very well by these robots. So that's all part of the underlying guarantees that we were formulating for. Those guarantees are actually encoded in theorems. Not going to talk about those over here. One of our main objectives was to come up with a method that is faster than mixed integer programming, that is computationally more tractable. These results are already 5 years old, so now the methods have gotten much faster, but the trend still holds. What you see over here is that for this particular reach avoid problem, we're looking at the amount of time that it takes for the optimization to terminate. As you increase the number of UAVs, you see that, of course, our method, which is the line shown in blue, does slow down, but it's looking like it's almost slowing down linearly with the number of drones, which, if you know anything about STL and mixed integer programming, is that the problem is actually exponential complexity. So empirically looking at this linear result looks really nice. The mixed integer programming based method actually does not scale very well. It works really fast for one robot, works okay for two robots. As you go up to four robots, the optimizations would actually time out. They would take more than 5 hours to solve. So at that point, we just stop. So it tells us that, yeah, our method does indeed work computationally as expected, that it's fast. And so all of these efforts in breaking the problem down into one of solving just for the waypoints does indeed result in good results. In fact, we're now orders of magnitude faster because we also have a C++ implementation as opposed to a MATLAB one. And yeah, over here, you can see that we're pretty much one order of magnitude faster than the results shown in the previous slide. So at this point, even for 8 UAVs for missions like this, we can solve for these trajectories in real time or in less than a fraction of a second. But that was a simple example. How do we actually get to much more complicated missions with longer horizons and richer STL specifications? How can we still solve for them? The answer is yes. But first, maybe let me introduce what I mean by more complex behaviors. So in STL, you can nest operators. That is, you can have operators within operators in a specification. One nesting is the always eventually nesting, which says, for example, shown over here, that always eventually phi, which means that this task phi should be satisfied repeatedly in these given time intervals. An example of that is that I want this robot to visit goal set 1 and goal set 2 in a repeated manner. So throughout 10 seconds, I need to visit goal set 1 at least every 2 seconds, and similarly for the second one. And so it would result in a trajectory that goes from goal 1 to goal 2, back to goal 1, and then cycles around. So desired behaviors like that can be encoded using STL. You can also have another type of nesting, which is eventually always, which says that I need to hold a behavior after doing it once. So an example over here is that the robot reaches a goal set and then stays there for the next 2 seconds. So it will result in a trajectory then that either stops or loops within goal 1. So something like that can also be encoded using STL. So one of the more complicated examples that we studied in one of our papers was that of hypothetical drone operations or simulated drone operations in the Philadelphia International Airport region. So we studied the problem in 3D. I'm showing you a 2D projection because it's easier to visualize. So in red are no-fly zones, like for example, over runways, over busy interchanges, and so on. In green are regions of interest that these UAVs should visit. In this particular mission, there are 5 UAVs. One of them is doing a loop between picking people up, passengers up from a parking terminal, taking them to an international terminal, and so on. There's another UAV that is doing the same thing. And there's UAVs 3 and 4 that are doing a package delivery from the DHL part of the airport to a nearby business complex. And then there's taxi, which is UAV 5, picks up a passenger, goes to a particular area. So all of this can be encoded in what looks like a very large STL specification, but our method can generate trajectories that do indeed satisfy these type of requirements. And shown over here is, again, the simulated trajectories being flown out. This video is sped up 10x. The actual horizon of the specification was of the order of tens of minutes. And you see this behavior where these robots go inside these green sets, and then you see them waiting over there for a while. That is because of the nesting of operators. So it's the robots going back to DHL, picking up more packages, flying out to the business complex, repeating it, and so on. So anyway, our proposed method that we were talking about, it's not only for toy problems, it can also scale to these type of larger motion planning problems. So what we've studied so far is a centralized optimization method to generate trajectories for multi-rotor robots such that they satisfy STL specifications. We only so far aimed for kinematic feasibility, but as robots get heavier or if they're flying more aggressive trajectories, we need to go beyond just kinematic feasibility and actually make sure that we're generating trajectories that can be tracked by our lower level controller as well. So the other part of the work that I did a couple of years ago was on coming up with both the trajectory planner and the tracking controller via a co-design, such that we have even stronger guarantees than what we had in the flyby logic work. So flyby logic only generates kinematically feasible trajectories. Now we're going to try to go beyond that. The key idea over here is to bring our tracking controller together with a trajectory planner. So a trajectory planner is, again, flyby logic. It's going to generate these trajectories that satisfy kinematic constraints. It's also going to give us a robustness value. That robustness value is going to serve as a worst case or a bound on the worst case tracking error for a tracking controller. What we'll do is in this tracking controller, we'll actually take into account the full nonlinear UAV dynamics, and we'll synthesize a feedback law. So it's going to be a nonlinear feedback controller that's going to actually respect the UAV dynamics and state and input constraints, as well as have an upper bound on the tracking error. So there's two components. Again, I'll try to go through this quickly in the interest of time. I won't get too much into the details. The trajectory planner, again, flyby logic, takes in the UAV kinematics, takes in the STL specification, takes in constraints on, for example, accelerations and jerks. And it works with a simple, again, an underlying simple kinematic model for 3D motion for each UAV. The second component that we're now designing that is new is a tracking controller that's going to look at the full nonlinear UAV dynamics. So an example of those are shown over here. So terms like mass and other components like moment of inertia will show up over here for the robot. It's a UAV, standard UAV model with 8 states. And what we're going to do is design a controller to minimize a notion of error. So this error is going to be computed over the trajectories that the planner created, or the position in X, position in Y, position in Z created by the planner, and the positions of the actual system in X, Y, Z, similarly for velocities. And it's going to do so while trying to minimize essentially your roll and pitch angles. So what we get by looking at this particular error is that we can work out control affine error dynamics for the system. As shown over here, this E dot is some function of E and U, and also X hat, which is the input of or the planner trajectory. So now what we want to do is minimize this tracking error subject to the input constraints and the dynamics shown above. So a problem like this can actually be formulated as a essentially sum of squares optimization. So what we're going to try to do is use those tools to synthesize a robust trajectory tracking controller that respects these bounds and takes in the constraints. Again, we'll synthesize that law using sum of squares optimization. And the type of guarantees that we'll have are that the upper bound on tracking error. So we actually have a time varying function for tracking error, but we can find a global upper bound delta for that. And also our control law, KE, is going to be such that as you feed in errors, it's going to only compute control inputs that are going to be within given bounds U bar and U lower bar. So we have some strong guarantees on this construction. Then for flyby logic, what we do is we essentially take delta, which is this worst case tracking error that we had from our controller, and enforce that as essentially add that to the lower bound of robustness that we were looking for. And it turns out if we can find a satisfying trajectory that is sufficiently robust, or that is more robust than epsilon tilde plus delta, then the resulting closed loop system is going to be something that we can actually track these trajectories using the controller KE, have continuous time STL satisfaction, and have UAV kinematic constraints being respected as well. So this is all formalized in a theorem that we have. Now we have stronger guarantees than just kinematic feasibility. We in fact have dynamic feasibility of these resulting trajectories. And yeah, the trick again is in co-designing this planner and controller together to account for the worst case that the controller would have done. The controller is a nice feedback law, so it doesn't need any computation online. It's just a nonlinear function in closed form. The way this would be implemented on a multi-UAV setup is that flyby logic would run as a centralized trajectory generator to spit out these trajectories that would be tracked on each robot that is going to be running this nonlinear feedback controller that we just synthesized using sum of squares optimization. And then it will generate essentially a thrust and a desired essentially roll and pitch angle that can be tracked by off-the-shelf controllers like PID controllers running on the robots that, in fact, for our experiments, we didn't even have to retune those PIDs on the robots. So I'll show you a simulation case study that shows this in action. This is over 4 UAVs. Think of them again as in teams of 2 each. The first team is going to do this repeated patrolling mission where they're going between zone 1 and zone 2 every 5 seconds. UAVs 3 and 4 are going to go to a delivery zone within the first 10 seconds and then, sorry, they're going to go to a deliver zone within the first 10 seconds and then go to the base, which is shown in pink, in the next 10 seconds. All these UAVs should, of course, always avoid the unsafe sets, not crash into each other, and so on. And this can be encoded in the following STL specification shown below. So again, writing these STL specifications does take some domain expertise, but once you write down the STL spec, the rest of the method is automatic. We automatically generate the objective, the constraints are formulated, even the low-level controllers are going to be synthesized using sum of squares optimization. So shown over here are 3 views of this particular simulation, including a top-down view. The dashed red lines show the planned trajectories for these robots. The blue lines show the actual trajectories as flown by our tracking controller. You see that they do indeed deviate, but they're always going to remain within a worst case or within a tracking error bound, which is shown with this 3D ellipsoid that is being centered at each of these UAVs. And the X, of course, shows the current position and orientation of the UAVs. What you see over here is that the trajectories are tracked close enough in a way that the resulting the 4 UAVs actually end up satisfying the underlying STL specification. And now we have strong guarantees on the fact that we generate trajectories that can be flown and tracked within a bounded error with our given co-design of the planner and controller. This is also, again, empirically verified when we look at the tracking error results for a particular UAV. So this is for UAV2 in these experiments. The dashed blue lines show the tracking error in the position or how close was the actual trajectory to the planned one. The red line shows the tracking error in the velocity component. And you see that they're well within the dashed pink and black lines, which are the robustness bound and the worst case tracking error for our controller. So the good news is that we can indeed track them. One thing we see over here is that the bounds are indeed conservative. So we can use notions of, we explored some work using online reachability to tighten these bounds, but it wasn't that huge again, so we didn't really follow that through. All right, so maybe I'll briefly pause for any questions. Now that I've talked about 2 of the main methods that I wanted to talk about. All right, if there are no questions.
So Yash, one question is, what about like, these disturbances like turbulence or, external disturbances due to, it could be at a fast time scale or a slow time scale of like a weather change?
Yeah, that's a great question. So in this particular work, we are, again, going with dynamics that we know perfectly. So if there are disturbances, we're not modeling them. The hope is that the robustness is big enough that if you did have disturbances, you still remain within the bounds as shown over here. So yeah, it's a good question. It's not something we deal with directly in this work. If there's time, I'll go through some of the ongoing work where we do talk about unmodeled disturbances and how we can, if we have some samples of what those disturbances look like, we can actually be robust to disturbances like wind. Turbulence is probably, it's hard to model with the kind of models that I'll show you later on with essentially Gaussian processes. But yeah, it's a good question. We somewhat try to deal with it as in some of the ongoing work.
Okay, thanks.
Yeah, thanks, Al. All right, so maybe in the interest of time, I'll probably skip most of the distributed trajectory planning method work, but what we've shown so far were methods that are all centralized. That is, there is a single think of a giant server that's solving this trajectory planning problem for all of the robots, and then telling the robots, hey, here's what the trajectory that you should fly out. We also developed this method with Rahul and Hussam called flyby distributed logic, which is how do you do this trajectory planning in a distributed manner where each robot is free to make its own decisions. So we're trying to solve the flyby logic problem by dividing robots into different groups. And I guess I'll skip the technical part, but the idea is each group solves, or each robot solves a simple convex sub-problem. So it's not solving the original non-convex optimization. And then after solving this subproblem, these robots are going to share their solutions with each other until some convergence. In fact, we do have proofs that our method is going to converge and is going to converge to a stationary point of the smooth robustness function. We also have another result that tells us that if the robustness is high enough, then we have the same type of guarantees as flyby logic. That is, you satisfy the STL spec and you have kinematically feasible trajectories being generated. All right, maybe I'll go through one result. So again, we go back to our benchmark reach avoid problem, where we want the robot to we want these UAVs to reach a goal set within 8 seconds. They want to always avoid the unsafe sets. They want to make sure they're not crashing into each other. And for something like this, again, we can solve it using now distributed flyby logic. So shown over here is a simulation for 4 UAVs. And it's not very interesting, but what you see over here is that all of them do indeed make it inside the goal set. In green, they're not flying into this unsafe region shown in the middle, and they're also not crashing into each other. And these trajectories also are going to respect the kinematic constraints that we had set out to respect initially. What's worth noting over here is that we're now, again, solving this in a distributed manner. And what we're going to do is a comparison with the centralized approach. So for this benchmark problem, we consider cases with 2, 4, and 8 UAVs. So FBL is going to be the centralized approach flyby logic. FPDL is the distributed version that I skipped over pretty much. And first, we're going to look at the time that it takes each of these methods to find a trajectory for each of these robots such that they satisfy the underlying specification. So you can see over here on the left, we have the satisfaction times for flyby logic. On the right, we have the times for the distributed method. And the trend over here is that the distributed method is in fact faster than the centralized method when it comes to finding trajectories that satisfy the underlying spec. So the good thing is the distributed method is indeed faster. Even for the time that it takes to find a set the solutions with the highest robustness values possible, the distributed method is faster. Take this result with a grain of salt because the centralized and the distributed method do have different convergence or exit criteria. So it's not really a very fair comparison, but the distributed method does dominate much faster. What we do pay for though is in terms of the robustness of solutions. So flyby logic, I did not quite mention, is the guarantees for that optimization is that we'll end up at a local optima of the smooth robustness landscape. With flyby distributed logic, we only get to an extreme point, which could also be a saddle point. And we do see that in practice a little bit, where flyby logic results in more robust, or the centralized method results in trajectories that are more robust. So they could tolerate larger disturbances than the trajectories generated by the distributed method. We can also take into account more complicated specifications. I guess we're getting close to time, so I'm going to skip all of that. And I'll talk about some of the ongoing work. Sorry. All right, so before I move on to the ongoing work, let me just quickly summarize all these methods that I propose for motion planning for multi-rotor systems or multi-agent multi-rotor systems with signal temporal logic objectives. We essentially propose flyby logic that is first a centralized method that has strong guarantees like kinematic feasibility. We also proposed a distributed method that has convergence guarantees and kinematic feasibility guarantees with it. We can also co-design the planner and controller to have even stronger guarantees, such as dynamic feasibility. And one of the main motivations behind these works was that we wanted to come up with methods that are computationally tractable and can be applied online to a wide variety of scenarios. Our methods empirically do indeed show that. And also, we can work with the full grammar of STL. So we can create any specification using STL, and our methods can, in theory, solve them. So that's kind of the summary for all this multi-agent motion planning with signal temporal logic. Some of the limitations there, though, of course, are that these methods, I only talked about the STL-based ones. So these are incomplete algorithms. That is, even if there may exist trajectories that satisfy the underlying specification, there is no guarantee that our methods will actually find them, which is a big drawback when it comes to having certifiably safe controllers. Also, in the distributed method, one thing I shoved under the rug was that the way these robots are communicating with each other is through an instantaneous and lossless method. In practice, we know no such communication medium exists, so we have to study our distributed method and formulate it in a way that actually is aware of the communication limitations. So that's part of ongoing work that I probably won't talk about today. Um, Also, even though initially in my very first slide I'd set out to talk about problems of motion planning with complex objectives in evolving and partially known environments, there is no such evolving or partially known environment um, in this particular set of methods that I talked about. So with that, we can move on to ongoing work where we try to overcome some of these limitations, like including the one that Rahul mentioned with other disturbances. So the first work is on the control of systems with partially known dynamics, where we want to satisfy STL objectives. For this particular setup with partially known dynamics, imagine we have, again, a UAV with dynamics that can be broken down into the nominal or known dynamics and some state dependent on model disturbance such as wind. And the impact of wind is going to depend on which angle you're facing or what's your angle of incidence with the wind and so on. So it's going to be a state dependent unmodeled disturbance. Our problem statement is such that is over here where we want to find again a sequence of control signals for these robots such that they generate a resulting trajectory that satisfies the underlying STL specification while being subject to these state-dependent unmodeled disturbances. The way we solve it, of course, is we can't just leave them as unmodeled disturbances. Otherwise, we're looking at worst case bounds and becomes a robust control problem. We've solved this in a data-driven approach. That is, we assume that we have access to some trajectories in this particular environment. That is, we have state and input sequences. What we're going to compute are the mismatches between the nominal model and what the actual state of the system ended up being, which essentially is due to this unmodeled disturbance. And we're going to learn these unmodeled disturbances using Gaussian processes. So using Gaussian processes for model predictive control has been around for a while. In fact, some of the seminal work came from Rahul's lab back in 2017. But what we're going to do is take Gaussian processes for our nominal dynamics and now try to solve this problem of STL satisfaction. I'm going to, again, not going to get into the details of how we do it. The work is still being prepared for submission, hopefully to CDC. The idea is that we try to formulate an optimization. We will try to solve this in a mixed integer programming way, but we propose approximations that actually allow us to solve this mixed integer program in a computationally tractable manner so that we can use this for real-time control. So you can have disturbances that are acting at a very fast time scale, like changing wind. I don't know if you could particularly handle something like turbulence, but if you have enough data samples and you have a good model of the disturbance, you can actually come up with methods, and our method does have some correctness guarantees associated with it. Another work that we're looking at is now where it's not the dynamics that are uncertain, but the environment is uncertain. So for that, we're going to look at the problem through the lens of trying to generate even higher level motion primitives. We're working, for example, in a grid world-like space. And our specifications now are going to be given to us via linear temporal logic. So the unknown part of the dynamics here is that we don't actually know the transition probabilities in this grid world that we're operating on. It's a challenging problem. We try to solve it using reinforcement learning, but it doesn't lend itself very naturally to reinforcement learning. I can talk about these details later if you're interested. What we propose is a method inspired by self-play, or the class of algorithms that were used for the game of Go or AlphaGo. But this is not a self-play problem. So we take that type of an approach, turn it into a single player problem, and we come up with policies or a method from which we can actually extract policies after training to come up with these higher level behaviors that satisfy an underlying STL spec. We beat some state-of-the-art benchmarks, including much more recent ones. I don't have all the slides for that. And we can also satisfy specifications that state-of-the-art methods could not satisfy, even in environments where we do not know the transition probabilities, or a robot could end up doing something that it was not planning for, but our method is still robust to that. Yeah, so I'm going to skip all of this. But what we're trying to do now is take some of these methods, apply them to a more realistic problem rather than just working on simple grid worlds, also make them robust to adversarial environments. And finally, a lot of our work is on taking the methods that I'm developing, putting them on ground robots. One of them is a Jeep Grand Cherokee that we have through a collaboration with Magna. It's running Autoware on it. The Jeep itself is giving us a lot of problems. So once we fix those, we expect to have a few Autoware demos done by the end of this term. And then there's other research that I did not talk about That's going to be implemented as trajectory tracking controllers over here, with our special focus being on working in essentially difficult environments such as the one shown over here, which is very common in Waterloo, where you have ice and snow on your roads. We also work with multi-agent or multi-robot experiments with this LimoBot, and we're also focusing on the problem of going fast and drifting as a part of F1 tent. So I guess with that, I'll stop and I'll leave some time for questions. But thank you all for your time, and I hope you got something out of this. Thanks.
Thank you, Yash. So we have time for some questions.
Quick question.
Yeah.
Do you need then a centralized control or at least monitoring so the agents know the position from each other, or they transmit this on a mesh like in near real time?
I see. That's a good question. So depends on how you want to use this planner. If you want to use it as a one-shot offline planner, in that case, all we need to know are the initial positions of the robots. So the centralized planner should know the initial state of all of the robots. We can also run this online, and in that case, all of the robots should actually be sending their positions back to the centralized controller. So yeah, the assumption is centralized controller knows everything at all times. For the distributed one, yeah, we do assume a mesh network where they can all talk to each other. And in that case, they actually need to communicate their solutions with all the other robots that are a part of the same specification.
Nice. So one more. Then
yeah.
What if it happens that I'm actually reporting my position incorrectly? Is there a way that you could add one more variable by say, hey, I have 2 or 3 agents that observe the position for, let's say, agent X plus 1, and that's not really their position, so it's actually incorrect position that was reported. But then you have 3 other agents that.
I see what you're saying. This is something that we're actually exploring as part of ongoing work. So I have a PhD student who joined in the fall term, and his work is on looking at this distributed method with more realistic assumptions. So one of those is also working with a more realistic setup. One of them is, what if you don't know the position of all the robots around you perfectly? How do you still operate? We haven't quite thought about information sharing, as in, like you said, there's 2 robots that observe a third one. They tell the fourth one about it. I think that could be a setup. What we're looking at is where you can have, you only have information shared when you're within line of sight of a robot, or if 2 robots are within line of sight of each other. So for something like that, we're developing methods for, again, being able to satisfy the spec. But yeah, what you're proposing is an interesting next step for that, but not something we've looked at yet.
Great. Any other questions, folks?
Hi, so this is Abhijit from Virginia Tech. First of all, like great presentation. I have a quick question in terms of like for unstructured environment, and particularly say that for like a disaster management kind of situations, what do you think is the current readiness of this kind of robot swarm?
Oh, that's a great question. And I would say in terms of technology readiness level, this would be pretty low, like a 2 or a 3. And that's on a scale of like 7. The reason why I say that is the type of methods that I talked about assume that you have the map known perfectly a priori. If you're talking about disaster management, let's say you want robots going inside a building that's collapsed or partially collapsed, you don't have the maps known to you. So in that case, this work is very limited. However, the type of work that I did not talk about, maybe in the bottom left side over here, we are working on methods, not so much with temporal logic as our behavioral specification language, but methods that can work in a priori unknown environments and also do tasks that were not seen before in your training data set. So for something like disaster management, that would be a good application for those type of methods. Fortunately, I did not have time to talk about that in detail today. But yeah, it's a great question. We are working on it, but not from the temporal logic lens.
Okay, thanks. So maybe another possible one is that for like maybe traffic disaster management, right? Where It's not necessarily that you need a building map, but means we know the roadway map of the system. So, and maybe going back to the previous question, that the information sharing and the protocols there. So is there still like some advancement there, and in terms of technology readiness?
Yeah, I think that's more of an application where this could perhaps be applied. Again, the challenge over there would be that the environment is maybe not known perfectly a priori, and these type of methods would still struggle with it, but that doesn't mean that it's the end of these type of methods. In fact, there is work from Boston University, I think a couple of years ago. There was this method called barrier net, which essentially is take control barrier functions, or take a neural network that is trained to behave like a control barrier function, and that can essentially be used as a filter for whatever our methods are proposing. And what that would mean is that if there's parts of the road network that are blocked that we did not know about before, the barrier net would kind of take care of this new, essentially unsafe zones, whereas our method would continue to provide the higher level trajectories for what's going on. So for something like that, yeah, you could stitch together methods, including ones that I propose, other work, and come up with a solution.
Yeah, thank you.
That's an interesting question. Yeah, thank you.
Great. Thank you, Yash, for a wonderful talk and the journey of using signal temporal logic, with multi-agent systems.
Thank you.
And we'll definitely post this recording online. And please feel free to reach out to Yash anytime. Yeah, thank you, everyone,
absolutely.
for attending this talk.
Thank you. Thanks, everyone. Thank you for all the interesting questions. See you.
Bye.
Thanks, Rahul. Thanks, everyone.